Hello everyone and welcome back. So in this video we're going to begin optimization on the Simplex noise, and we may just knock out both 2D and 3D in this one video. It won't be quite as bad. Let me go ahead and give this to you, Lee.
Right.
There you go.
Yep. Now with simplex noise, it's going to be easy because there's not a whole lot that we need to optimize. But conversely, because there's not a lot to optimize, we're not going to see that much performance increase. If we look at the 2D simplex noise, the optimizations left to be done are getting rid of these dot products. There's only 3 of them though. So that means we're not optimizing nearly as much as we are with the Perlin noise, which had 4 and 8 dot products and 7 lerps. There's also no lerps in here. So we're only going to see a marginal bit of optimization. But we've already gone through and explained how to do dot products, so we're just going to go through and inline those dot products. So we'll start off with our grad 3, paste that in, dot x times x0 plus our grad 3 copied again times y times y0. So
Now, do you want to go ahead and put those in parentheses?
Well, it's not going to matter because of the order of precedence, but we can. So we can put those in parentheses, and I'm also going to copy this whole thing. Actually, I'm going to copy it with the comments, so I can comment all 3 of them. So that will take care of those. This is GI1 now, so I want to modify these. This one's GI2. Modify those. These are X1, and I'm not even going to copy those. It'll be just faster to type these.
So you're saying the result, we all know my math is horrible. The result would be the same if you did like T2 times grad 3.
No, you're right.
Okay, because I was having a really hard time seeing mentally how that would work.
No, I forgot about the the addition in the middle of it. It's like, oh no, multiply by multiply is all the same no matter how you do it. Oh, yeah, there's
sure.
an add in there.
Okay, cool.
All right, so now that takes care of our 2D. I'm going to copy the first part of this because down here in our 3D, we're going to start off with the same thing. But we need to add the third part of this. So we're going to add the grad3.z times z0. So this gives us our dot product for our third, or our 3D noise.
Grab the comment too.
Oh yeah, good catch. Put a space in there. So we'll copy that. Now this time we've got to do it 4 times. And again, it's not that much. So this one only has 4 dot products. So we're not going to see as much of a return. But we will see some improvement. All right, now I'm going to turn on insert. So turn off insert. Otherwise, that'll come back to haunt me. All right. Let's go ahead and get rid of this so we can test 2D. Go ahead and hit play. This should fire up into Simplex. Right click, make sure we're still in Simplex. So
Around
we're looking
34.
at 33, 34.
Okay.
So that's 3D.
No, that was 2D.
Oh yeah, you're right, 2D. Because I turned that off. I wish it was 3D, because then that would be really fast. All right. And this should be 3D.
About 47.
At 47. So what did you say? 34?
34. And
Yeah.
47.
All right. And let's get our super Wampanoine Mr. Calculator out. So 34 divided by 49. And then subtract that from 1. Gives us 30.6. So a little bit more performance back than value, but not quite as much as Perlin. Actually, not even close to what we get back for Perlin.
Yeah, for sure.
Which is what we expected. And then 47 divided by 56. And then subtract 1 from that. And a measly 16.1%.
Every little bit, you know?
Yeah. It's still substantial. It's almost 10 milliseconds. So, but compared to the optimizations that we got for all the other ones, it's the lowest return. Now, that's not to say that that is all the optimizations that could possibly be done with this. I'm sure there's a lot more, but that gets into really fancy math that I don't understand. I mean, you could probably get away somehow with, instead of doing multiply, some sort of bit shifting and, you know, throwing this thing into some sort of quantum wormhole to get it going faster. So if you're like a math whiz and you can get these things going even faster, let me know. I'm definitely interested. But there are other implementations out there, other ways of accomplishing the same thing. These were just based off of the white papers and websites that I found as being the easiest to implement, and then we just tried to make them as fast as we could. And the end goal was to end up with a noise or a noise class, or with 3 different noise algorithms, both in 2D and 3D, that looked good and ran fast. And that's what we ended up with. So I just wanted to get to the point where they were, you know, as optimized as we could make them.
Right.
And then make sure that everybody else knew how to do it.
Now, as far as the errata goes, is that it for this section? Or I know we have another thing, but I think that might be an errata for session 6.
Right. Even this wasn't really so much the errata. The first errata was the actual true bug in the noise.
Right.
This was just kind of a, let's get this even faster than before.
Sure.
And we gave, probably about a week and a half, 2 weeks for people to get their versions optimized. So
yeah, about that.
And we want to show you how to do it. Now, there is another set of videos we'll be doing next, which is going to be covering, I don't know if it'll be one or multiple, but it'll be covering something that I found while I was experimenting with the way Unity calculates tangents compared to the way that we were calculating tangents, which was kind of interesting because I brought in a mesh from Maya which went through the
Oh,
Unity.
we can explain all that in
Oh
that video
yeah,
where it's
yeah,
very
yeah.
specific.
Yeah, sorry, my bad. I'm
No, it's
getting
all
carried
good.
away.
But okay, well, with that, that's going to wrap up this video, and then off camera, we'll just discuss how we want to name that next one. But that will conclude getting all of the optimization for our noise in place. Thanks a lot, everyone.